Hi everybody, welcome to 9.7 Taylor approximations. So this is the first day we're going to spend on Taylor approximations, and what we're really going to look at is we're going to create polynomials, all right, and we're going to use those polynomial functions to approximate actual functions, all right. So we're gonna go through our first example here where we have a function f of x equals e to the x, and we're gonna come up with a polynomial function that correlates with it. And in class I'll kind of show you how the graphs become more and more similar. The functions become more and more similar the more terms we add to our polynomial function. So for instance, we're going to use this polynomial p sub n of x. That n just represents what degree we're really looking for, okay? And it equals this guy right here, a naught plus a1x plus a2x squared plus a3x cubed, so on and so forth. And we're going to create this polynomial to approximate our function e to the x, all right? So this first example is really just showing you how do we come up with the polynomial to represent e to the x, okay? So I'm going to kind of zoom in a little bit here. And the first thing we would need to do is if I wanted to find P0 of x, all right, meaning that's just our first term here. It's that A0 or A naught. It's our y-intercept. So in order to kind of figure that out, if this is our polynomial, well, if we let x equal 0 in this polynomial, we're just going to be left with this right here, okay, this A naught. So we can say, all right, well, that means f of 0 is going to be the same as p of 0, okay? So when we plug 0 in for f, right, e to the 0, we just get 1. When we plug 0 into the p, this polynomial, all these terms with x go away, and we're just left with this a naught. And so we get this a naught to be 1. So what we would say is the polynomial p0 of x equals 1. So that's the first term of our polynomial. But that's not going to be very accurate, right? If we were to graph that, that's just a horizontal line at y equals 1. So we need more accuracy, so we need to add some more terms to this polynomial. So if I find p1, so a degree 1 polynomial, this is a degree 0 polynomial, that's going to be a0 or a naught plus a1x. Okay, well, we already know what a naught is, right? How do we get this a1 by itself? Well, if we take the derivative of this polynomial, right, then this a naught goes away, and this a1 is all by itself, okay? And then the rest of the terms have x's in them. So we can find the first derivative of the polynomial and plug 0 in for x, so all the other terms that have x in them go away, and again, we're just left with e to the 0 equals a1. And we'll have to take the derivative of f as well, okay? Because remember, we're using the polynomial to approximate this function itself. So we get a1 to be 1. So then this polynomial, the first degree polynomial, is going to be our a naught value 1, plus the a1 is the coefficient of x. So it's just really 1x, or just x. Okay, so now we've got a linear equation, right? But if we're comparing that to the graph of e to the x, it's still not quite. And again, I'll show this in class so we can see a live action of how this polynomial starts looking more and more like our curve. So let's keep going. Let's find the second degree polynomial, okay? So the second degree polynomial, p2 of x, is just these three terms, a0 plus a1x plus a2x squared. Well, in order to get a2 without this x, we're going to need to take the second derivative. The first derivative, this guy goes away. Second derivative, this term will go away. And now we're just going to be left with 2a2, okay? So the second derivative of f is e to the x, or e to the 0 when we plug 0 in for x. And the second derivative of the polynomial here, the second degree polynomial, is going to be 2a2, right? So when we solve, e to the 0 is 1, we divide by 2, we get the a2 value. So then the second degree polynomial is going to be 1 plus x plus 1 over 2 x squared, or x squared over 2. Okay? But to get even more accurate, let's find the third degree polynomial. Okay? So to find the third degree polynomial, again, we already know a0, we know a1, we know a2. We need to get a3 all by itself. So if we take the third derivative of the polynomial, let's just kind of walk through this. When I take the first derivative, and I'm just focusing on this term here, we get 3a3x squared. Okay, well, I still have an x. So take the second derivative. Now we're at 6a3x. Now we take the third derivative, and we're at 6a3. Okay, so now we can plug 0 into the third derivative of f and the third derivative of p. Well, the derivative of e to the x is e to the x, so the third derivative of f of 0 is going to be e to the 0, which is just 1. And the third derivative of p is 6a3. So we can get a3 to be 1/6. So then the third degree polynomial is going to be 1 plus x plus 1/2 x squared plus 1/6 x cubed. So what you might notice is a pattern, okay? If we were to keep adding terms, find the fourth degree polynomial, the fifth degree, sixth degree, etc., what we might recognize is we could rewrite the function e to the x as this polynomial right here. So the first term that we found is 1 plus x squared over 2. And what's another way to write 6? It's 3 factorial. So we would get x cubed over 3 factorial if we went backwards. This 2 is the same as saying 2 factorial. And this x term here is like saying x over 1 factorial. So what we notice is the degree matches the factorial in the denominator. And we would keep going on. So what we can get is we can get the function f of x equals e to the x, and we can rewrite it as a polynomial function. So like I said in class, we're going to compare these and see how accurate our polynomial is to the curve of e to the x. Okay? So our goal today is to take functions and write them as polynomials. So this leads us to the Nth Taylor Polynomial. Okay, so the Nth Taylor polynomial, if f has n derivatives at some value c, then the polynomial can be, or we can write the polynomial as p nth degree, so an nth degree polynomial, is equal to f of that c value plus f prime of that c value times x minus c plus f double prime of c over 2 factorial times x minus c squared, so on and so forth, plus the nth derivative of f at c over n factorial times x minus c to the n power. So this is called the Nth Taylor polynomial for f at c. There's a special type of Taylor polynomial, and that's called a Mclaren polynomial. And this is when c equals 0. Okay, so a Mclaren polynomial is when we're evaluating it when c equals 0. And so it's very similar, but instead of the x minus c's, it's just x, okay, because c is 0, or x squared, or x to the nth. And instead of f of c or f prime of c, it's f of 0, f prime of 0. Those are the coefficients of our terms, okay? So this is called a Mclaren polynomial for f. Let's move on to some examples where we can really find some polynomial functions to approximate. Okay, let's suppose we want to approximate f of x equals cosine of x using a Taylor polynomial. Or in this case, since it's at x equals 0, this would be a Mclaren polynomial. Okay? Now, here is our cosine function. all right? And what we want to do is we're going to create a polynomial function, and the more terms we add, the closer this blue graph gets to the red graph, especially at 0, because that's where we want to evaluate at. Okay, so what we do is we just kind of create a table to organize our work, because our goal is we need to find the coefficients of our terms. Okay, we need to find the f prime of 0, f of 0, f prime of 0, f double prime, triple prime, quadruple prime. Okay, so f of x is cosine of x. We want to evaluate at x equals c, where c equals 0. All right, so the cosine of 0 is 1. This represents our constant term. F prime of x is going to be negative sine of x. When we evaluate that at 0, so negative sine of 0 is 0. This is the coefficient of our linear term x. So f double prime is going to be negative cosine of x. When we evaluate that at x equals 0, cosine of 0 is 1, times negative 1, we get negative 1. This is the coefficient of the x squared, that quadratic term. F triple prime of x equals sine of x. Sine of x at x equals 0 is 0. This is the coefficient of our x cubed term. Then when we take the derivative of again, so the fourth derivative, we get cosine of x. And when we evaluate that at x equals 0, we're back to 1. So now we're just back to this same pattern here. Okay, this is the coefficient of the x to the fourth term. So what we should notice is all of the odd degree terms have coefficients of 0. All of the even degree terms, their signs are alternating. Positive, negative, positive, and so on and so forth. So what we can do is we can write a polynomial approximation for the function f of x equals cosine of x. So we would have 1 minus, our coefficient is 1, so x squared over 2, plus x to the fourth over 4 factorial, using that Mclaren polynomial, minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, and we can continue this pattern on forever. So this is the Mclaren approximation, or the Taylor approximation when x equals, or c equals 0, of the function f of x equals cosine of x. Okay? All right, our next example, now we are going to construct a specific type of polynomial, okay, to approximate the function f of x equals ln of x. So they told us a Taylor polynomial, all right, it's a degree 4. So being a degree 4, that means that we want the fourth degree polynomial. Okay, that's what that's saying. So we want P4, and since x equals 1, this is like our c equals 1 value. So we're going to create this Taylor polynomial, degree 4, to approximate ln of x near x equals 1. So we're going to evaluate this when x equals c, which is equal to 1. Okay, so it's centered at 1. All right, so we create our table of values. Now, since we only want P4, I need to go up to the fourth derivative. Okay, the fourth derivative of f. So, as we go through, we know f of c equals ln of c. Again, when we evaluate that at c equals 1, ln of 1 is 0. This is our constant term. Okay, f prime of c is going to be 1 over c, and I'm going to rewrite it as c to the negative 1 so that we can come up with the next derivatives pretty easily. When we evaluate c at 1, 1 over 1 is just 1. So this is the coefficient of our linear term. Okay. Second derivative, we get negative c to the negative 2. Evaluating that at c equals 1, we get negative 1. This is the coefficient of our quadratic term. F triple prime, so the third derivative, is going to be 2c to the negative 3. Evaluating that at c equals 1, we get 2. This is the coefficient of the cubic term. The fourth derivative of f is negative 6c to the negative 4. Evaluating that at 1, we get negative 6. This is the coefficient of the quartic term. All right, so now just a reminder, our Taylor polynomial for P4, all right, the fourth degree polynomial is equal to this f of c plus f prime of c over 1 factorial times x minus c plus f double prime of c over 2 factorial times x minus c squared, etc., etc. Okay, so now what we're going to do is we're going to plug in what we know, and we're going to simplify. Okay? All right. So the coefficient of our constant, or our constant term, is 0. So f of c is 0. F prime of c is 1 over 1 factorial times x minus our c value is 1. Plus negative 1 is the coefficient over 2 factorial, or just 2, times x minus 1 squared. Plus the coefficient of our cubic term is 2 over 3 factorial times x minus 1 cubed. Plus negative 6 is the coefficient of our quartic term over 4 factorial times x minus 1 to the 4th. So now we just have to go through and clean up these coefficients with the factorials as well. And when we do, we get our Taylor approximation, the fourth degree Taylor approximation, as x minus 1, that's this guy here, minus x minus 1 squared over 2. 2 over 3 factorial is going to simplify to 1 over 3, and so you have x minus 1 cubed over 3. Negative 6 over 4 factorial simplifies as 1 over 4, well, negative 1, so negative x minus 1 to the 4th over 4. So this is the fourth degree polynomial approximation, right, to approximate the function f of x equals ln of x. So what we're getting here is our red graph here is ln of x. And as we continue to add more terms, so this is the fourth degree polynomial, and you can see at x equals 1, we're pretty accurate. They're pretty much the same curve here. We'll show this real time again in class. Let's now look at error. Okay, so far we have come up with Taylor polynomials, right? But now we can talk about how we use those Taylor polynomials to actually evaluate or estimate a certain value. Okay, so we can use this Taylor polynomial to estimate a certain value. So for instance, if we're going to estimate the square root of 4.1 without a calculator, or maybe with a calculator, right? Okay, so first we need to talk about this remainder theorem. All right, Taylor's theorem, this error and remainder, all right, this is the absolute value of the remainder, okay, is equal to the absolute value of f of x minus that nth degree polynomial that is the approximation. So f of x is the actual value. The polynomial is the estimated value, okay? So the difference between those is known as our error, okay? That's the error. So that's how kind of close we were. The estimate, this is Taylor's theorem right here, okay? And we're going to get more into this in the next video, all right, where we're going to talk about what this represents. So Taylor's theorem, this remainder, is equal to the n plus 1 derivative at z, okay, over n plus 1 factorial times x minus c to the n plus 1 term degree. Okay, so the remainder, or the error, using n terms is at most the maximum possible next term. The z value maximizes the derivative and must be between x and c inclusive. Again, we're going to talk more about this aspect in the next video. We're going to first just talk about the error, okay, in this example here. So if we want to estimate the square root of 4.1 using a third degree polynomial where f of x equals x, the square root of x plus 1, around c equals 3. Okay, so just as a reference, P3, a Taylor polynomial, all right, third degree polynomial is going to be this right here. So this just kind of helps us visualize what we need. So we'll need to get up to the third derivative to help with that coefficient of that cubic term. So we do our table, and we're evaluating this when c equals 3. So we know f of c is the square root of x plus 1, or c plus 1 to the 1/2. All right, evaluating that at c equals 3, we get 2. So this is our value there. F prime of c is this guy here. When we evaluate that at c equals 3, we get 1/4. So f prime of c is 1/4. F double prime is this guy right here. Evaluating that at 3, we get -1/32. So that's our coefficient here. The third derivative is this guy right here. When we evaluate that at c equals 3, we get 3/256. So that's our coefficient of that last term of our third degree polynomial. Okay? So we're going to use that in just a second. So now we need to get into the actual estimate. So we want to estimate the square root of 4.1. Well, we can rewrite this as the square root of 3.1 plus x, because we're using the function the square root of x plus 1. So in this case, we can let x equal 3.1, okay? So when we then take x minus c, because that's what our, that should be a c there, I apologize. Up here in our polynomial, that should be a c. Okay, so when we evaluate that polynomial, at x minus c, it's really 3.1 minus 3, or simply 0.01. So instead of this x minus c throughout, we're just going to substitute 0.1 in there, okay? So using our table of values from the left for our coefficients of our polynomial, our first term is 2, coefficient of that second term is 1/4, times that x minus c, or 0.1, minus the coefficient 1/32 over 2 factorial times 0.1 squared, plus that last coefficient 3/256 over 3 factorial times 0.1 cubed. Now, you probably will be using a calculator to plug all of these in and see that we get the Taylor approximation for the third degree Taylor approximation. We get 2.024857111. Okay, so what that means is we just used our polynomial to approximate the square root of 4.1 as this value here. Okay, so let's find out what our error is. All right, so our error is the absolute value of the actual, so f of 3.1, so we would plug the square root of 4.1 on our calculator, minus the approximation that we just found up above, okay? And when we do that on our calculator, we get this error of 0.00000029993. So we're actually pretty close to what the actual value of the square root of 4.1 is. All right, if you have questions, let me know.